Hello everyone. In this lecture, we'll try to integrate all different pathways together by looking at these various organs and tissues and how they interact with one another in the control of metabolism. And there's only one learning outcome for this session. You may read it for yourself. And these are the questions you should be able to answer after this lecture, such as how do we maintain glucose during fasting? What are the changes to glucose, fatty acid, ketone bodies during a prolonged fasting? So which hormones are involved in the regulation of metabolism and how is glucose conserved for the brain during fasting? And what are the roles of fatty acids and ketone bodies as the alternative fuels for glucose molecules? Okay, these are the four important organs or tissues in metabolism. And let's look at the first one, which is your liver. So the liver plays a central role in metabolism as it can metabolize a wide range of substrates and macromolecules, whereas other tissues can only metabolize a limited range of substrates. While for the adipose tissue, it is the major energy store or storage as it stores all excess nutrients in fats, which is in the form of triglyceride or triacylglycerol. So you can either store or degrade triglycerides in time of need. Now, how about the muscle? For the muscle, it is very important because it represents a high proportion of body weight and hence a high consumption on different substrates under different physiological states. So during a fat state, muscle uptakes a lot of glucose. So it uses part of the glucose for ATP production, while the rest will be converted into glycogen. However, when we fast, muscle can use other substrates such as the fatty acids or ketone bodies so that glucose is conserved for the brain. So how about the brain? Well, for the brain, it is an organ that loves sugar very much because the brain lives predominantly on sugars. And unless during critical conditions, it will only utilize ketone bodies. So when the blood sugar drops, which organ do you think will suffer the most? Well, the answer is the brain. Therefore, hypoglycemia is a medical emergency because it impacts your brain function. Let's look at what happens during the fat state. First, the absorbed glucose from the intestine is sent to your liver through the portal vein. Then part of it is converted into glycogen for storage, while the excess will be converted into fats, which will then be transported by the VLDL or the very low density lipoprotein and stored eventually in adipose as the triacylglycerol molecule. But don't forget that you also get glucose from a small intestine directly, and this majority of sugars can get into the bloodstream, supplying the needs of your brain, kidneys, and your muscle. So when there is an excess of glucose in your plasma due to overeating or the lack of exercise, this condition is known as hyperglycemia. As a consequence, insulin will be secreted to promote the uptake of glucose by your muscle tissue and converted eventually into glycogen for storage purposes. But what happens during the fasting state? Well, your liver is going to maintain glucose level by breaking down the glycogen into glucose molecules. So they will top up your bloodstream for a moment. But when the glycogen stores is running out during a prolonged fasting, your adipose will respond by undergoing lipolysis, which is the breakdown of triacylglycerol into its building blocks, which are glycerol and fatty acid. So glycerol can be used for gluconeogenesis or the synthesis of new glucose molecules, while fatty acids can undergo beta oxidation for the production of ATPs. And when the fatty acid is transported into your liver, it can then be converted into ketone bodies, which is another fuel molecule that can be used by your brain and your muscle. But regardless of the presence of ketone bodies, we have to maintain blood sugar level more than 5 millimolar because that is the minimum level by which the brain can function. As such, depending on the metabolic need, our body might start breaking down muscles to produce amino acids in the form of alanine, which can then again be used in gluconeogenesis, so to top up the blood sugar level. This table summarizes the changes in glucose, fatty acids, and ketone bodies during a prolonged fasting of 8 days. Well, starvation means there is no food but only with water intake. So we began with a glucose level of 5.5 millimolar but ended at 3.5 millimolar, which is equivalent to a 36% reduction. You might think that it is a big fluctuation, but if you look at fatty acids, it increased by 600%. Even more for ketone bodies, they increased by 500 folds. So what do these data suggest? Well, they suggest that glucose homeostasis has already kicked in at the expense of both fatty acids and ketone bodies, serving as the alternative fuels so that glucose can be conserved for brain function. Okay, this man over here held the longest record of fasting because he didn't eat for more than 1 year, and to be very specific, 382 days, but he survived healthily. But technically, he was fed with some vitamins, minerals, and yeast extracts because we need those components as core factors and core enzymes for our enzymes to function optimally. So, how did he survive? Well, by lipolysis as well as ketosis. Okay, if you're going to look at the data of fatty acid and ketone bodies during a long fasting, you'll see that fatty acid only increase to a certain point and never go beyond 2 millimolar. Why is it so? Because fatty acid is not water soluble and therefore it cannot dissolve in your blood plasma. As a result, it is transported along with the human serum albumin as a complex molecule. So the limiting factor here is the albumin because we only have about 4% of serum albumin. And how about 3-hydroxybutyrate? What is this molecule? Well, it is a ketone body. So is it water soluble? Yes. And that explains why you got a big jump in your 3-hydroxybutyrate during starvation, but a small increase for the fatty acid.